which is the smaller part of the solution. And there's also the solvent, which is the larger part of the solution. So remember, those two really do make up an entire solution, the solute being, again, that smaller part, which a lot of times is a solid. So for example, as we talked about, if you were making a sodium chloride solution, you would weigh out some solid sodium chloride, you would put it into, maybe a beaker or something like that, or maybe a flask, and put some water in it and dissolve it, the water being the solvent. And then when you have it obviously all dissolved, we do have a solution, which obviously is a homogeneous mixture. And remember, those solutions typically do have that aqueous symbol next to it. And as we talked about, sort of the difference between aqueous and liquid, liquid is sort of just a pure sort of substance. Something like water by itself would be a liquid. But when we dissolve something in it, like sodium chloride, we do get this solution. Again, remember that usually the name of the solution is pretty much the solute. So if you have a sodium chloride solution, that would be your solute. You had a magnesium chloride solution, that also would be your solute as well. We also talked about sort of solubility and sort of the idea of like dissolves like when we talk about sort of making solutions or just solubility in general. And if you remember, what that really refers to is those intermolecular forces that we talked about in the previous chapter. So in terms of things like dispersion forces, hydrogen bonding, dipole-dipole interaction. And as we talked about, really things that have a way to interact with themselves very similar to other things. So things that use hydrogen bonding, reacting with something that actually uses hydrogen bonding as well, makes things very, very soluble in each other. So it's only really when you sort of cross over and you have two things that really are trying to use sort of different intermolecular forces that they really do run into trouble. So as we talked about last time, those are things like ionic and polar guys. Those are usually soluble in each other. You have something that's polar and polar. They are also soluble in each other. Again, they're going to both be using perhaps either hydrogen bonding, you're going to be using dipole-dipole interaction. And we also talked about, what sometimes throws people, is the idea that nonpolar and nonpolar guys are also going to be soluble in each other. Again, these guys are going to be using those dispersion forces. They both are using very similar intermolecular forces, which is going to allow them to interact really well with each other. Again, really, as you cross over between sort of polar and non-polar, you do run into some trouble here. Those guys are typically going to be insoluble in each other. Again, really for that difference in intermolecular forces. One, for example, is going to try to be using dipole-dipole like we talked about, maybe hydrogen bonding. Other one's going to be using dispersion forces, which are those relatively weak type forces that we talked about. And again, over a long period of time, they really have no way to maintain their interaction between each other. So they typically end up being pretty non-polar. We also, towards the end, got into sort of a conversation about concentration and ways to describe solutions. And in addition to things being a saturated solution, which means, again, it contains a relatively maximum amount of solute that you could dissolve at a given temperature. We also talked about unsaturated solutions, which means you could continue to dissolve the solute until you hit a saturated solution. We also talked about concentrations. So we saw some percent concentrations, like percent mass to mass, which is our mass of our solute divided by the mass of the solution times 100%. We also saw some other ones that are sort of percent concentrations, percent volume to volume, which is basically the volume of the solute over the volume of the solution. We also saw mass to volume percent, which is the mass of the solute over the volume of the solution. So we did a couple of problems with those. Again, remember that the main one of those three, the bottom part here, what's on the screen, is the mass of the solution is really important. You want to make sure that you get both the solute and the solvent when you basically do that problem. Again, very common in those problems that you're given that information sort of separately from each other. And last, we sort of finished up talking about molarity last time. Molarity is moles per liter, moles of solute per liter of solution. And remember, we could really use this sort of like a formula as well. Liters would equal moles divided by molarity. And if we want moles, that would be liters times molarity. And again, this is a very common sort of three ways that we do use molarity, especially moles, using it by liters times molarity, and also finding the volume by taking the moles divided by the molarity. So those are really important things. And lastly, right, we talked about the idea that you do oftentimes in calculations want to really kind of use both of those units when you're doing those calculations. As we talked about last time, a lot of times people leave the big M and they sort of forget all about the volume part or the liters part in the calculation. And a lot of times, they run into trouble. They're not really sure, it's the liters on top, liters on the bottom. So again, if you kind of just take out that big M, as we talked about, you really will be probably in a better shape when you do those calculations. So that's sort of what we covered last time. Any questions on any of that stuff there before we continue on? Okay, so if you do have questions, remember you can always ask and put it in the chat box as well if you would like to do that. So we're going to pick up here where we sort of left off. We're going to go to talk about what happens with concentrations of ions. So sometimes, we're maybe not interested in calculating the molarity of the entire ionic substance. Perhaps we're interested in really just calculating perhaps the ions of each, or the concentration of each of the ions that are present. And we could do that with molarity, and we could do it based on how that ionic compound basically breaks apart. So if we take something like calcium chloride, when it does break apart, we will get basically one calcium ion for every two chloride ions. So it's almost a 2-to-1 sort of situation, twice as concentrated in the chloride ions as it is in the calcium, ions. So we really could almost take a sort of stoichiometry sort of approach to this and look at the coefficients, basically 1 here, right? 1 and obviously 2. And if we wanted to sort of relate the concentration of just the ions here, we could take the concentration of the whole thing. And since it's a 1-to-1 relationship between calcium chloride and just the calcium ions, the concentration of just the calcium ions would actually be the same concentration. We basically would take 1 times 0.2 molar. Now, that's different as we were talking about here with the chloride. We do get basically 2 chloride ions for every 1 calcium chloride unit that basically comes there and breaks apart. And we would actually then multiply the concentration of the whole thing by 2. And that's sort of the simplest way to figure out the concentration of the ions. But really what we're doing here is we are using really a mole to mole relationship between the whole thing and each of the ions. So we could actually take the formula and really come up with sort of 2 sort of conversion factors. We could say that for every 1 mole of the whole thing, we do get 1 mole of calcium ions. We could also say for every 1 mole of the whole thing there, we get 2 moles of the chloride ions. So this is really what we're doing here down on the bottom. And to show you sort of the actual long calculation here with sort of the mole to mole relationship, we could start with our 0.25 moles of calcium chloride per liter. Remember, the big M is moles per liter. And we really could just do sort of a conversion problem here. We could go for every 1 mole of the whole thing, we get 1 mole of calcium ions. And obviously, as we see here, we end up with 0.25 moles per liter of calcium ions, which is exactly what we got down here. And that's also why down here, if we started with our 0.25 moles per liter of the whole thing, we could use our conversion factor that we got for how it breaks apart and go for every 1 mole of the whole thing, there is 2 moles of Cl minus. Again, moles of the whole thing will cancel, going to get us to our Cl minus, and we end up with 0.5 moles per liter of chloride ions. So that's basically what we're doing when we sort of multiply. Hey, we're going to take 1 times concentration because it breaks apart into 1, or take 2 times the concentration because it breaks apart into 2 ions. That's sort of the long version. So a lot of times people will sort of do this sort of short version and just go, okay, it breaks apart into 1, multiply by 1, breaks apart into 2, multiply the concentration by 2 for that ion. Hey, if it breaks apart into 3, multiply it by 3. So again, you could do it sort of the longer way here, which is really what you're doing when we do this sort of short version of the calculation here. It really is, again, sort of that mole to mole relationship. We're really breaking apart or canceling out the units and doing some dimensional analysis. Any questions on how we got to that there? So let's take a look at another sort of example of this. If we look at potassium phosphate, and remember, these are ionic compounds. So really when they go for a swim, right, they're not going to stay together. They're going to break apart into their ions in that solution. So really where we want to start with, again, is how it breaks apart. So we see here that, again, for every one of the whole units here, potassium phosphate, we do get 3 potassium ions. And also for every one of the potassium phosphates, we get 1 of the phosphate ions. So again, really, if we were sort of looking at our mole-to-mole relationship, for every 1 mole of the whole thing here, we get 3 moles of the potassium ions. And for every 1 mole of the whole thing, we get 1 mole of the phosphate ions. So again, you could do the long calculation like we just talked about, where if you started with 0.25 molar of the potassium phosphate, and again, this will break it into moles per liter. We see that we have, for every 1 mole of this guy, we get 3 moles of potassium ions. Again, the moles of the whole thing's going to cancel. And if we multiply basically by 3 is what we're doing, we end up with 0.75 molar for the potassium ions. Again, doing sort of the same calculation there, we get a 1-to-1 relationship for our phosphate. And again, just to show the longer calculation part, 0.25 moles per liter of the whole thing, using the formula really as a conversion factor to get rid of the whole thing. We got 1 mole of it to 1 mole of phosphate. Obviously, essentially multiplying by 1, which gives us our 0.25 moles per liter of our phosphate. Any questions on that? So again, a lot of times, sometimes you're not necessarily asked about the entire ionic compound. You may just be interested in what the real concentration of those ions are floating around that solution. So remember, again, when these guys are in that solution, it's pretty much what you got. You got some potassium ions floating around, you got some phosphate ions floating around, and perhaps it's important to know what the concentrations of each of those are. Maybe you want to add something to a solution to maybe precipitate out just one of the ions. So it's good to know sort of those concentrations, so you know perhaps what to add, the concentration, what you need to add to maybe do something like that. Any questions on how we go from sort of the whole ionic compound to the concentrations of just the ions? Okay. All right, so why don't you give one a go here? So we have aluminum bromide. Why don't we do both? So let's figure out what is the molarity of the bromide ions and also the aluminum ions. So take a minute or two and see if you come up with that. It's actually the next couple of questions, I think. So we'll just do them together here. So take a minute or two and see what you come up with. We're looking for the molarity of the aluminum bromide solution, each of the ions that are present. So the concentration of the aluminum ion and the concentration of the bromide ion. Okay, so let's take a look and see how we're doing. So first off, obviously, the most important thing is we want to make sure that we do get, obviously, the correct formula for this. So this goes back to what we talked about, obviously, with ionic compounds. We have a -1 for our bromide, a +3 for our aluminum. So again, the first important part here is the correct formula of AlBr3 in terms of our correct ionic compound. At this point, we also should know that when it will break apart, that means we are going to get 1 aluminum and 3 bromides ions that basically will occur. So this really does set up our relationship that we talked about. We see that for every 1 mole of aluminum bromide, we get 1 mole of aluminum ions. And also we can see that for every 1 mole of our aluminum bromide, we get 3 moles of our bromide ions. So that's sort of our two relationships that we have going on here. And we can start with, we'll start with the bromide, which is this question here. So 0.5 moles per liter of AlBr3. Again, if we sort of take the longer approach here in terms of our calculation, we see that 1 mole of AlBr3 gives us, we're going to do bromide, so 3 moles of our Br minus. Again, the moles here will cancel, and we're essentially taking, sort of like the shortcut there, 0.5 times 3, going to give us 1.5 moles per liter of our bromide ions. So this answer here would be C for the bromide, which is what it's asking for. We could do the exact same thing here for our aluminum. It's going to be 0.5 moles of the whole thing per liter. Again, it's a 1-to-1 relationship, 1 mole of the whole thing here, giving us 1 mole of aluminum ions, going to get us 0.5 moles per liter of aluminum ions in this case. And that's, I think, the answer to the next question there. First off, any questions on sort of the long part of the calculation here? Yeah, so it's not necessarily, Faith, a decomposition reaction. What's really happening here is in the solution, what we have going on is when we do put this ionic compound in this solution, it's really not going to stay together. It's going to break apart into aluminum ions and bromine ions. And basically what's happening is sort of what we talked about. I'm going to just go to the next one so we have a little bit more room. What's happening is when those aluminum ions go into solution, right, it's going to be surrounded by water, right? And water is polar, as we talked about. So it's going to be surrounded by the negative side of water. My wonderful artistic drawing here. There we go. Draw some water molecules around it. While basically when our bromide ions go into solution, it's also going to be surrounded by water, but it's going to be the positive side of water, which is the hydrogen side and stuff like that. So really what we're looking at here is not necessarily a decomposition reaction. It's not really a reaction sort of happening. Remember, a chemical reaction means that we're going to really be producing some new substance. And that's not really happening here. We're really just dissolving a solid, for example, in a solution in these type of problems. And you remember that it's not really more a physical change, because as we also talked about earlier, if we start heating this off, right, all these water guys are going to go away. We're going to evaporate off the water, and then our ions will be free to come back together. So in terms of sort of how the ionic compound breaks apart, you can sort of think about it as sort of breaking apart, not necessarily really a decomposition reaction. It's just sort of what happens when it goes into a solvent and it basically dissolves. Other questions on that? You're welcome. So again, that's sort of like as we talked about in the previous one, the long approach to doing these calculations. There is really nothing wrong, and most people will sort of just do the quicker approach, where essentially you just think about how it does break apart in solution and go, okay, this is 0.5 molar. So this is basically 1 times the 0.5 molar for this guy. This guy breaks apart into 3 times the 0.5 molar. But I did want to sort of show you the longer part of the calculation, so you really understand sort of how we go from the whole thing to just the ions. And again, it really is sort of like stoichiometry, that mole to mole relationship. Other questions on this? Okay, so why don't you take a minute or so here and see what you come up with this one. We're looking for which solution here actually has the greatest number of ions. So again, a hint to how maybe to approach it is to think about, the total moles of ions that you have floating around that solution, positive ions, negative ions in each of these. So take a minute or two and see what you come up with, and then we'll talk about it. Okay, so let's take a look and kind of see how we could approach it. So we'll kind of look at it the same way since we just were talking about sort of the concentrations of the ions. So the first thing we could do is really look at each of these sort of solutions individually and figure out, what is the concentration of each of the ions that are present. So if we have sodium chloride, as we talked about previously, it will break apart into a sodium ion and a chloride ion, which means if we sort of do our little quicker calculation in terms of molarity, it is a 1-to-1 relationship between sodium chloride and sodium ions and sodium chloride and the chloride ions. So we essentially would multiply the 0.1 by 1, which would give us 0.1 molar for our sodium ions and also 0.1 molar for our chloride ions. Again, it's a 1-to-1 relationship, so we'll multiply each of the concentrations by 1. If we look at something like calcium chloride, when it breaks apart, we get 1 calcium ion and 2 chloride ions. So remember, when it kind of breaks apart, the 2 goes in front. So in terms of its concentration, if this is 0.1 molar, the calcium is a 1-to-1 relationship, which means you take 1 times 0.1 molar, which would give you 0.1 molar. But the chloride is a 1-to-2 relationship. So for our chloride, we would take 2 times 0.1 molar, and that would get us 0.2 molar for our chloride ions in that case. We could do the same thing for our iron 3 chloride. So FeCl3 going to break apart into 1 iron 3 ion and 3 chloride ions. Again, in terms of how that relates to our concentration, this whole thing is 0.1. It's a 1-to-1 relationship between the whole thing and the iron 3, which gives us 0.1 molar for our iron 3. It's a 1-to-3 relationship for our chloride, excuse me, which gives us 3 times 0.1 molar, which gives us 0.3 molar. So at this point, we have sort of the concentrations of each of our ions. We can now really figure out the moles of everybody, and we're going to use our molarity, which is our moles per liter divided by liters. So that means that our moles would be liters times molarity. So we do have to do a little conversion for our volume here for everybody. We do need to divide it by 1,000 or move the decimal point 3 places to the left. So if we did divide 400 by 1,000, we end up with our 0.4 liters, 0.3 liters, 0.2 liters, and 0.8 liters. Now, this last one, which is sucrose, is basically sugar, which is carbons, hydrogens, and oxygens. This guy here is held together by obviously covalent bonding. It's actually not going to make any ions in that particular case. So we don't have any way for that guy, obviously, to break apart into ions in that particular case. So what we have now is the molarity of each of the ions. We also have the volume of each of the ions. So we basically, for each solution, can figure out the total moles of each of those guys. So I'm just going to go next page here and do that. So for our sodium chloride solution, we have 0.4 liters times our molarity of our sodium, which was 0.1 moles per liter of sodium ions. And that's going to get us 0.4 times 0.1, 0.04 moles of sodium ions. We're going to do the same calculation for our chloride, and 0.04 liters times also our 0.1 moles of chloride per liter, going to give us 0.04 moles of chloride ions. So grand total of ions floating around in terms of moles in the sodium chloride solution going to be 0.08 moles. So our total moles. We could do similar calculations for our other guys there. So we had for our calcium chloride, we had 0.3 liters times the molarity of the calcium ions that we calculated, which was 0.1 moles per liter of calcium, going to get us 0.3 times 0.1, 0.03 moles of calcium. We'll do the same thing there for our chloride. So 0.3 liters times our chloride, which remember was 2 times the concentration. So that is 0.2 moles per liter of chloride. And that's going to get us 0.3 times 0.2, 0.06 moles And if we do an addition there, grand total here for our calcium chloride solution, if we sort of add those guys together, we're going to get 0.09 moles total. And lastly here, if we sort of do our iron 3 chloride, where we had 0.2 liters of it, using the molarity of the iron, which was 0.1. Going to get us 0.2 times 0.1 gets us 0.02 moles of our iron 3. And let's move a couple things out of my way here. There we go. 0.2 liters times our chloride in that case, which was 0.3 moles per liter of our chloride. And 0.2 times 0.3 going to give us 0.06 moles of chloride. Grand total on that solution, 0.08 moles basically floating around. The last one, which is sucrose, obviously is not going to contain any ions because, again, it's more covalent. So we wouldn't even really have to worry about that in terms of ions. So in comparison to this, what we do see is it is the calcium chloride solution here that has basically more moles of ions floating around that solution than the other two. Actually, the sodium chloride solution and the iron 3 chloride solution ends up with this same total number of moles. Any questions on how we got there? So it looks like the answer there was B. It looks like the winner. Any question on that calculation? Again, how to go from sort of the whole thing to just the ions? Any questions on that? Or going from obviously molarity and volume to moles as well. That's also a very common calculation. You do it a lot, taking molarity and volume to go to moles, especially as we'll talk about towards the end of this chapter with solution stoichiometry. Very, very common calculation used a lot. Any questions on any of those there? Okay, so why don't you give this one a go here. We're looking for how many moles of chloride ions are there in 60 milliliters of a 2 molar magnesium chloride solution. So take a couple of minutes here and we'll talk about it. Okay, so let's take a look here. So again, we're not interested in the whole thing. We're interested in just the chloride ions. So much like we talked about before, we want to make sure we start with the proper formula here, or we're not going to really get that right relationship. So magnesium, which is group 2, has a +2 charge. Chloride, which is chlorine, is group 7, has a -1 charge. So again, when we put those together, we want no charge. So we are looking at MgCl2 as our ionic compound. That means that when it does break apart and go for a swim there in the solution, it is going to make a magnesium with a +2 charge, and we are going to get a couple of chloride ions. So we're interested in moles, and we do have molarity given to us. So again, if you're not sure sort of where you should be going with this, you could think about molarity. And obviously, we do have the volume given to us. We do have the molarity. So as the problem asked, moles is definitely what we're looking for here. So we would want to solve for moles, which as we just saw is liters times molarity. But again, we're not interested in the whole thing, which we do have the concentration for, which is 2 molar. We're interested in just the chloride ions. So as we saw before, we could see that the relationship is for every 1 mole of the whole thing, we do get 2 moles of the chloride ions. So we really could use that as sort of a conversion factor here. So in order to get to moles to do that, we do have to use the volume and the molarity. So we do have to do a conversion. So we have 60 milliliters. We want to convert it into liters. So we could divide by 1,000, or you can move the decimal place 3 places over, going to give you 0.06 liters when you do that. So now we have our 0.06 liters. So we could start with that and do a little dimensional analysis here. So 0.0600 liters. We could use the concentration of the whole thing, which is 2 molar. So remember when it says 2 molar, big M, that is the same as 2 moles per liter. So we could use it like that here. So 2 moles per liter of the whole thing. And at this point, if we stopped right at this point, the liters would cancel and we would be moles of the entire thing, which is magnesium chloride, which is close to what we're looking for, but we are looking for just the chloride part. So again, this is where we could use the formula as a conversion factor to go for the whole thing to just the chloride ions. So in 1 mole of the whole thing, we get 2 moles of the chloride ions. And again, this is magnesium chloride up here. So our moles will cancel, leaving us moles of just the chloride, which is what we're looking for. And it looks like we go with 0.06. We're going to multiply everything up there on top times 2. And times 2 one more time. There we go. And again, get us 0.0. I'm not 0. Say that right. 0.24. There we go. Moles of chloride in that particular case. Any questions on sort of that calculation there? Again, if you kind of want to do it a little quicker, you could have done our kind of 2 times 2 here and ended up with 4 molar for our chloride ions and really just started with 0.06 liters times our 4 moles per liter of chloride ions. And as you can see, you end up with the same answer in this particular case. So again, you could do that kind of quick way to get to the concentration of just the chloride and then basically just do a liters times molarity calculation at that point. Any questions on any of those 2 ways of doing it? Again, whichever way you're more comfortable with. Sometimes the longer way is a little bit better in the sense that you could kind of see everything canceling out. But as long as you understand sort of the relationship of concentration and how it breaks apart into ions, the short way, can be a saver in terms of time as well. Any questions on any of that there? Okay, so let's take a look at the next one here together. So we want to know how many grams of sodium chloride is dissolved in 50 milliliters of a 1.25 molar sodium chloride solution. So here we're looking for really how many grams we need to go kind of scoop out to make this solution. So again, if you're not really sure where you might want to begin, looking at molarity, since we do have molarity given to us. We don't have liters given to us, but we do have milliliters given to us, which is just as good. So again, the only thing we don't really have in terms of molarity is moles. So that's a really good place to kind of start this calculation with, because we can use the volume and the molarity to get to moles. And as we know, we then can go from moles to grams, which is ultimately what we're looking for by using the molar mass from the periodic table. So, that's sort of the way to kind of take this calculation. Again, if you're not sure where to go, because you don't really see grams or anything like that, always good to sort of mark off what they give you and then kind of continue the calculation. So we'll start with this part right here to get to our moles of sodium chloride. Sodium chloride obviously being NaCl. We do have to convert our volume into liters. So again, taking our 50 milliliters and dividing by 1,000, moving our decimal place really 3 places to our left. We now can use the moles of sodium chloride will equal our volume, which is 0.05 liters. Using our molarity here, again, the big M, meaning that we have 1.25 moles per liter. Again, always good to kind of use both of those units in these calculations. Again, I can't tell you how many times I've seen people have no clue where that part is. So it's always good to kind of use both of them in the calculation of our sodium chloride. Liters here are going to cancel, and that's going to get us moles of sodium chloride. So if we take 0.05, we times it by 1.25, we end up with something like 0.0625 moles of sodium chloride. In this particular case, we actually are interested in the whole thing. We've done a couple examples. We're interested in just the ions, but we are interested in the whole thing. So our last step here is to go from now moles to grams using the molar mass from the periodic table. So if we look up there, we got for our sodium 2299 grams per mole for our sodium, plus our 3545 grams per mole for our chloride. And if we add that together, we end up with 2299 plus 3545, 5844 grams per mole. And remember, we're really going to use that as a conversion factor as well. So taking the moles of sodium chloride that we need. Moles are on top, so we're going to put moles on the bottom with our molar mass so everything cancels out. Oops, and write the right number there, 5844 grams. Moles of sodium chloride will cancel, and we will end up with something like 3.65 grams of sodium chloride is necessary to make this solution here. So what does that number sort of really mean? What it means is if I were going to make the solution of sodium chloride, I would go to the balance, I would scoop out 3.65 grams of sodium chloride. Again, I would put it maybe in an Erlenmeyer flask, in a beaker. Beaker, not the greatest to truly measure for solutions, but to start to dissolve it. Put a little bit of water in the beaker, get it to dissolve, maybe pour it into a volumetric flask, fill it to the top there to the line. And after all my sodium chloride has dissolved, and I put in exactly 50 milliliters of water, basically, I will end up with a solution that has a molarity of 1.25. Any questions on the calculation or what the numbers really mean or anything like that? Where we got any of the numbers? Okay, so then why don't you give it a go here yourself and see how you do? Let's take a look at the next example. So suppose you were asked to prepare 150 milliliters of a zero point 0.1 molar sodium ion solution using sodium sulfate as your source. How many grams of the salt would you need to weigh out to basically get a solution that is 0.01 molar? Take a few minutes here and work on it. I'm going to give you some numbers that might be helpful. Here's sodium, which is 2299 grams per mole. We have sulfur, which is 3207 grams per mole, and oxygen, which is 16 grams per mole. All right, so take a few minutes here and see what you come up with, then we'll talk about it. And obviously, if you have questions, feel free to ask. Okay, so let's take a look and see what we're dealing with here. So again, we're looking really to sort of make a solution that has a certain concentration of sodium ions. And we're trying to make this solution from sodium sulfate. So again, since we're not really interested, perhaps ultimately in the end, you know, the concentration of the sodium sulfate. We are interested in just the sodium ions. We want it at a certain relationship. We are going to use this like we did before as sort of a relationship to figure out that mole to mole relationship between the whole thing and perhaps just the sodium ions. So when this breaks apart, we do get two sodium ions here and we get one sulfate ion. So we can see from that relationship that for every 1 mole of the whole thing, we do get 2 moles of just the sodium ions. And in this particular case, if we look at the information sort of given to us in terms of molarity, again, we do have the volume given to us. We obviously do have the molarity. So we can find the moles, but it's going to be the moles of the sodium ions in this particular case. So in this case, we're actually going to be kind of going the opposite way. We're going to go back from the sodium ions back to sort of the source of them to figure out how much we need to weigh out. So our goal here is to perhaps start with figuring out the moles of the sodium ions by using the liters times the molarity, as that's the information that's given to us. And then we could use this mole to mole relationship to go from just the sodium ions back to the whole sodium sulfate. And at that point, once we have the moles, we could use the molar mass to get to grams. So that's sort of the pathway we're going to be kind of approaching here. So we'll start with the first part here. We do again need to convert this into liters. So remember, whenever you're using volume and molarity, you do need liters for the units to cancel out correctly. If you multiply molarity by milliliters, you actually don't get moles. You get something known as millimoles. So that's an important distinction. Sometimes people think we could just go straight there. It's good. And you really can't in this case because, again, you're going to be off by that factor. So we do need to want to make sure it's always safe to convert it into liters so you don't run into any of those sort of issues. So we're going to basically divide by 1,000 or move our decimal point. So we got 0.15 liters in this case by dividing by 1,000 or just moving the decimal. We're going to use the molarity of our sodium ions, which is 0.0100. That's a lot of zeros there. One more zero. Moles of per liter of our sodium ions. If we stop right here and multiply this, the liters of sodium ions will cancel out. And we will end up with 0.15 times 0.01. We'll call it 0.0015 moles of sodium ions. So remember that although we do have the moles of sodium ions, we're ultimately looking for really how much to weigh out of this guy. So we now need to go from sodium ions to the entire thing of sodium sulfate. And that's where we're going to use our relationship here to do that. So we're going to go 0.0015 moles of sodium ions. Again, using the formula really as a conversion factor, we see we get 2 moles of sodium ions for every 1 mole of our sodium sulfate here. So we're going to divide that by 2, going to get us 0.00075 moles of sodium sulfate. First off, any questions up to that point here? So usually, right, it's not very helpful moles if we're going to say the balance and trying to scoop it out. We want some type of unit that we can relate to, which is grams. So we do need to figure out the molar mass here of our sodium sulfate. So that's going to be 2 times 2299 for our sodium, plus 3207 for our sulfur, plus 4 times our 16 here for our oxygen. And it looks like we will end up with it's like 142.1 grams per mole. And remember, we're going to use this really as a conversion factor. So taking our moles that we need of the whole thing, using our molar mass that we just calculated as our conversion factor, remembering to put grams up on top because that's ultimately what we're looking for here. Moles will cancel, and it looks like we would need to weigh out something like 0.1065 grams of sodium sulfate. Any questions on that calculation, where any numbers come from, where we got any relationships from, or anything like that? So again, what this means in reality is if you were going to try to make this solution that has a concentration of 0.01 molar in sodium ions that are floating around in there, you would need to scoop out about 0.1065 grams of sodium sulfate, dissolve it in enough water to make a total solution that's 150 milliliters. And again, if you mix it around, you should have a concentration of sodium ions in that solution that's sort of floating around that has a concentration of 0.01 molar. Any questions on that there? Okay. All right, so why don't you try this one here? We're actually mixing two hydrochloric acid solutions together. If we mix 225 milliliters of a 2.5 molar hydrochloric acid solution with 150 milliliters of a 0.75 molar hydrochloric acid solution, what is the molarity of the final kind of mixture once you kind of pour them in there together? So I'll give you some hints here. What you want to probably do is figure out the total moles of HCl that's going to be in there. We're going to have a certain amount of moles supplied by this solution. We're also going to have a certain amount of moles supplied by this solution as well. And remember that molarity will change with volume. So we want the total volume in this case. So once both of those guys kind of go for a swim, in the final solution here, we're going to have a final volume of 375 milliliters. So take a minute or two and see what you come up with. Again, trying to find out what is sort of the combined concentration of our new solution after we pour both of these guys into it. Okay, so let's take a look and see how you're doing. So again, as I mentioned, we're basically going to be dumping two hydrochloric acid solutions into the same container. So, they're each going to really supply a certain amount of HCl's, moles of it from each of those solutions. So say if we call the first guy solution A, we dump it in, it's going to supply some HCl, which in reality is going to be some H pluses floating around, Cl minuses floating around in that solution. Also, if we call the other one solution B, also dumping in there, it's going to supply a certain amount of moles of HCl. And when we give it a good kind of mix, shaky, right, it's going to become sort of all one solution at that point, and it's going to basically have a total moles of HCl supplied by each of those solutions. And it's also, as we talked about here at the beginning of the problem, going to end up with a new total volume. So when we think about the molarity of the kind of mixed solution, if you will, is moles per liter. We really do have the bottom part here, which is the total volume coming from both of the solutions together. Again, we get that by really just adding the 225 and the 150 to give us our 375. So the top part is the moles that we need to figure out how many moles we get really from each of the solutions that we dump in there. So again, we're looking for moles, which means we're going to take our liters times molarity. And we're going to do that for each solution. So we'll just call it solution A here. So solution A, again, we're going to convert our volume into liters. So we're going to divide by 1,000 or move our decimal place over. We're going to use the molarity of our first solution, which that 2.5 means 2.5 moles per liter of HCl. Again, the liters are going to cancel each other out, going to get us 0.2250 times 2.5 gets us something like we'll call it 0.5625 moles. We won't round too much right now, coming from our first solution. Our second solution, again, also going to provide us some moles. So our second solution was 150 milliliters. Again, we want to make sure we get that into liters by dividing by 1,000 or just moving our decimal point. We're going to multiply by the second concentration, which is 0.75. And from our second solution, we're going to basically be supplying to the overall solution something like 0.1125 moles of HCl. Any questions up to that point? Again, we're just really trying to find how many total moles of HCl basically went in for a swim into that solution. So to finish that part out, we do want to just really add them together. And if we take our 0.1125 plus our 0.5625, gives us a total moles that are really in that solution of 0.675 moles of HCl. And again, that 0.675 moles of HCl represents how many moles of that HCl that's swimming around in this sort of combined solution up here where we dumped everybody into. So now we have the total moles of the HCl swimming around in there. We have the total volume swimming. We can figure out the molarity, which is moles per liter. So we'll take our moles of 0.675 moles. We'll divide it by the liters of our solution. So we want to divide by 1,000 or move the decimal. And if we do all that, 0.675 divided by 0.375, we're going to end up with 1.8 moles per liter here. And again, you can either do that or you can write 1.8 big M. Again, this would be HCl in this particular case. Any questions on that? Now, in terms of perhaps significant figure wise, we did have 2 sig figs times 4 sig figs here. So along the way, 2 sig figs is really what we should have had kind of over here, which would have kept us to right about here. And then obviously when we divided here, we would end up with our 2 sig figs along the way in this calculation. So it really does come back from this sort of calculation or that part of the calculation at that point. So in this case, again, if you took those two solutions, you mix them together, we would end up with a combined molarity of that solution of 1.8. And that's something to keep in mind, as we'll see next, leading into sort of our next topic coming up in this chapter, which is dilution. That molarity, again, is moles of solute per liter of solution. So really, even when you add just perhaps not two different or two of the same solutions, or just add something like more water, again, we're increasing the bottom part of molarity there, the liters of solution, which means the molarity actually comes down, and it does change as you change the volume or add more volume to a solution. Molarity continues to change. What doesn't change, though, as we will talk about a little bit later on, and as you continue on in your chemistry career, is the moles part. So when you dump in these moles, there's a certain amount of moles that are swimming around in that solution, regardless if you just keep dumping more water in there or not. There's sort of a finite amount of moles that you supply to that solution, and that's really what sort of does the reacting when we add something else to it. It's those moles that are floating around in that solution. That's what's there, really available to do some type of reaction that takes place. Any questions on that calculation, or sort of molarity in general, figuring out moles, liters, molarity of the whole thing, ions, how much to weigh out? Any questions on any of that stuff? Okay, so again, making a standard solution, whoops, it's kind of like what we saw in the lab that we did last week, where you had to make they made a solution that was of a specific molarity and a specific volume and how much you has to weigh out. And again, as we saw sort of in the video, there's sort of some steps that you want to follow. Obviously, you can use the molarity and the volume and the molar mass to really figure out how many grams of the solute you need to weigh out. And that's really where you want to start with your solution, is, do that calculation like we've just been doing to figure out, how many grams you physically got to go to the balance and weigh out. Typically what we want to do a lot of times also, as you maybe saw in the video, is a lot of times people will take that solid and kind of put it into a beaker with some water and sort of pre-dissolve it a little bit. And again, that's really helpful, and there's nothing wrong with doing that, because you can get a glass stirring rod in there if you like, and really kind of give it a good mix. And as long as you don't put more water in that beaker than your total volume of your solution, you'll be fine. But really, when you want to make a solution that's really accurately known, you do want to use the right pieces of glassware. So as we saw in that video last week, this again is a volumetric flask. Volumetric, in addition to meaning very expensive, you should never break those things, they usually do have only one marking on it. And for example, right here, that line is the marking for the actual volume of it. So if that was, say, 150 milliliter flask, it would be 150 milliliters in terms of the total volume when you get to that line. In a lot of cases, when we do use volumetric glassware, we oftentimes do go to a couple of decimal places there in terms of when we record the volume and using it. So what we typically do, if you kind of do a pre-dissolve, or if you kind of scoop just the solid into your volumetric flask, we then would fill it with some water. And as you can kind of see, or your solvent, usually, again, very important when you use this glassware, is not necessary to fill it to the neck. Usually you want to kind of keep it below the neck there. And what that does in those sort of flasks is it gives you enough room to kind of give it some mixing. A lot of times you get to the kind of the neck of the flask before everything is sort of already dissolved. It makes it really hard to get all the solid to dissolve. So it's oftentimes very important when you use these type of glassware, if you don't do sort of a pre-dissolve and you do put the solid directly in it, keeps that solvent level kind of in the bottom part, gives you enough area to really mix it and get everything to dissolve in it. And then the most important part is, at that point, once everything's sort of dissolved, if you're using water as your solvent, you can carefully add it. Usually a wash bottle is a good thing to use, or something like that. And again, you do want to kind of usually stop before the line. And either, if you have really good control with your wash bottle, you could do drops, or sometimes people will take like a medicine dropper or something like that. And it's really important to make sure that the meniscus does hit the line. So kind of like what we saw in the video, she was very careful to try to keep it right at the line. And the important part is, a lot of times when people use this, sometimes it happens a lot. They go and they're trying to get to the line, and all of a sudden they find themselves like way up here, and they go, oh shoot, I kind of went over the line a little bit. No problem. I'll just take some of that solution and pour it off and get myself back down to the line. And that's probably not a good idea because you probably want to have the right concentration in here because remember all your solute has been dissolved. So when you kind of pour some of that out the top there, you're going to lose some of that dissolved solute at that point. And depending on how much water you kind of put in there, and you might not have the correct concentration in your solution. So that's why it's really important to really go sort of slow and make sure that you do hit it sort of right at the line. Any questions on sort of the steps there to make a solution? Okay, I think this is probably a good place to stop for today. Any questions on anything that we talked about? Okay, so coming up in lab, we have an experiment coming up this week, I think, which is some titration experiments and some more about solutions. So we'll talk about that. Maybe we continue to do some lecturing as well, just to make sure we're in sort of in the right place. So if you haven't done so already, please make sure you put here in the chat, and I'll see everybody in about 15 minutes when